thanks for the introduction. So I'm going to talk a little bit about learning machine learning this evening. And here is a DOI for this talk. So if you're ever interested later to find it, that's where you can look it up online. So let's see here. So I'm going to talk about 4 things in this presentation. The first is I'll give you sort of the idea of machine learning. Then I'll talk about ways to learn more about machine learning, and then I'll talk about how to study machine learning in the St. Martin's Masters in Mechanical Engineering program. And finally, I'll end with some of the work that I do that's related to machine learning. So we'll start out, there's sort of a progression here. We'll talk about machine intelligence in general to start. And, of course, we need to define what we mean by intelligence. Intelligence is the ability to map perceptions to performant actions. Now, I'm a robotics guy, so I think of machine learning as being something applied to robotics. And for me, perceptions and actions are the inputs and the outputs. But in general, inputs to outputs is what people talk about. So, machine intelligence, or artificial intelligence, AI, is our attempt to build intelligence into our technological artifacts. Feedback control systems were perhaps the first artificially intelligent systems, near and dear to my heart, having studied control systems for my graduate work. Here, a machine's designer need not know everything that will happen in their machine, so it's something that adapts, and so it's sort of the first variety of intelligence that we see in technology. And some of the early control systems actually go back to water clocks, purely mechanical instantiations like in steam engines. So these ideas have really been around for quite a while if you realize that feedback control theory really started quite a long time ago, or at least the practice of it. I don't know about the theory. So obviously computers have become the key technology of AI. Computer-connected systems can sense, remember, and reason, and that's sort of the foundation of intelligent behavior. Designing intelligence. This is sort of the first in a progression of moves that we'll make in going from generally how do we think about designing intelligence to deep learning being the most advanced topic we'll discuss. So early AI research attempted to directly program intelligence. This is similar to how technology worked before AI. The designer needed to accurately predict possible scenarios, which works pretty well in specific instances and simple worlds. So even playing chess, there are a lot of possible moves, a lot of possible positions of the board, and we know that AI, of course, has beaten humans at chess. Early on, those successes of doing things in very small, simple worlds were as sort of as well as we could do. However, Moravec's paradox arose in the late 80s. So this is a quote from him. It has become clear that it is comparatively easy to make computers exhibit adult-level performance in solving problems on intelligence tests or playing checkers, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. So, perception, locomotion, manipulation, natural language processing, and other human toddler level functioning broke the original conception of AI as purely symbolical, logical, and directly programmable. So, unfortunately, these things that are easy for humans to do turned out to be very challenging for artificial intelligence or machine intelligence. So we see down here in the figure, percepts go in. We have some human-designed program that hopefully allows this system to operate intelligently in its actions. Now we go to classical machine learning. The AI field then studied basic biological intelligence, such as insect intelligence. Turned out we needed to really go back to the basics there. A major result is that intelligence is tightly coupled to learning. Okay, so having something that appears intelligent without it learning is apparently not easy to do. Proved to be very challenging for us to do, at least. So here's a definition of learning. It's the process of increasing intelligence from experience. Machine learning is the broad field of technologies that learn from experience. Classical machine learning designers manually program features important for the problem. Okay, so aspects of the problem that are important. Machine learning algorithms then train a mapping from percept feature to action based on often what we call labeled percepts for which the right action is given. This data is called training data. So we put in some percepts, some data, some sensor information, and we then have the machine, the program, learn on these examples when they're given the right answer. So they develop better and better results the more training data they're given. Performance is measured by trying the mapping on testing data, which is also labeled. So we also know the answers to the testing data, but we didn't train our algorithm, our machine learning machine on this data. So we want to see how it does on data that it didn't train on. And this is sort of a much better test than giving it the same data that it trained on. Of course, it's sort of cheating it. In some ways, even something that's not very intelligent, that just looks up the answer, would be able to behave intelligently on data it had already seen before. So the sort of flow here is that percepts come in, the human-designed features are plucked out. And those could be colors, shapes in an image. They could be acceleration profiles or velocity profiles in different sensor data, or any number of things from the sensor data, things that we think are important from the data. The human designed these features and says, okay, these are the features that matter for this learning problem. And then we have a mapping from those features that are extracted by the human, or at least programmed in by the human, to say, okay, these are the things that matter. The machine learning algorithm trains then how to map those features to actions. And this is quite successful. This was, originally some of the early gains in machine learning. And the basic building blocks that we typically use, not every machine learning algorithm is a neural network, but neural networks tend to be the most popular type of machine that we use to do that mapping. So in this learned mapping, we would have a neural network. There are lots of varieties, but for now, we'll just say a neural network. Representation or feature learning. The choice of percept or input representation, comprised of features, so those features we talked about make up a representation, has a significant impact on the performance of machine learning systems. Representation or feature learning learns not only how to map designer-determined features to actions, but also which features are important. In this sense, it learns representations or features themselves. Significant improvements can be made with this technique. The human designer of features sometimes has really good insight, but other times they don't know. Or it's a new problem that has really, people don't have experience with, and they don't know which features are going to be important for this learning process. So learning the features themselves is actually a very powerful method, and that's sort of the I don't know, we could call it the machine learning 2.0 type of scheme. So whereas before we had human designed features, then a learned mapping, now we have learned features and a learned mapping. So we're expanding the domain of the learning algorithms here. And we finally get to deep learning, which is, the sexy term that people like to throw around. But it has a specific meaning, and we'll try to explain what that is from a very high level. So the first term to be aware of is factors of variation. And these are those aspects of percept data that are most important for performance. Okay, those are the important features. Or important aspects of the features, I should say. So most factors of variation are entangled within multiple features. So we might have, for instance, X and Y accelerometer data, but maybe what's important is some mixing of X and Y, and that's really the key feature here, or the key factor. It's a factor of variation. Maybe when it's equal to the root sum square of X and Y, maybe there's some sort of arc that's created in the data. And if you just looked at X, if you just looked at Y, if you just looked at those features, you wouldn't necessarily see it. So what deep learning does is it disentangles these factors by making layers of representation, with shallower layers using simpler representations and deeper layers using more complex or abstract representations. And so now we have a third box that we've included here. So we're learning simple features, and we're learning abstract features. And these abstract features or complex features are actually building on the simple features. So the simple features are learned, and the abstract features are learned from those simple features. And it turns out that these, adding these layers, it was thought for quite a while that you couldn't, that it would mathematically not help to include additional layers. But the key insight somebody made a couple decades ago now was that if you included a nonlinear function between each layer, you could actually have multiple layers of a neural network, which is usually the machines that we use to do these learning of features. So we can have multiple layers that tune into different features, and that tune in from sort of simple features to more abstract features that build up. And then finally, from those abstract features, we have to also learn a mapping to actions. So just like we originally had in machine learning. So this is the sort of the deep learning example that I'll give you. So this is an illustration. It's meant to sort of show you the idea here. So we have some input or data or percept, which is a photo of my dog Pepper, who is the cutest little thing ever. And I put this into a deep learning algorithm, and the initial representation of an image in these types of algorithms tends to be pixel numbers and color value. So we break it down into individual pixels, and we go from there. Okay, so we've got this input data, this photo. We break it down into pixels. That's the initial representation. And then we start to learn additional representations. And these are the deeper and deeper layers of the network. And so we first start with something that's relatively simple to identify, which are edges. Okay, they can be identified by comparing nearby pixels and seeing contrasts in color or brightness. And so edges can be plucked out. The next layer of complexity is contours or corners. So you can see sort of complex shapes starting to emerge here in this layer. And then finally, you can compose those complex shapes into object parts. So you'll say, okay, here's, for instance, a snout. Here might be a paw. Here might be an eye. And then finally, once you've got that deepest layer, then you have to map that to the output or the action. So in this case, you're identifying what is in a photo. You're doing image recognition. And the correct answer in this case would, of course, be dog. Cat or fox would be possible, maybe similar types of objects that it would try to recognize. So this is kind of showing the depth and how it builds in complexity from simple edges to complex parts of objects in specifically an image recognition example, which are the types of examples that people usually start out with in machine learning when they start doing machine learning. So this is kind of a review of what we covered here. So we started out with the non-machine learning AI, where we tried to hand design a program that took percepts to actions. Then we started to use machine learning, but we had to hand design or human design the features in. That was great, but we found that actually having a learning algorithm learn which features are important in a given representation was actually better in most cases. Finally, we put in these simple feature and abstract or complex feature layers, and we got deep learning in that way. So, we use neural networks. The bigger the data set, the better. The better the data set, the better too. If it's not a quality data set, then you can run into problems. And so this is kind of a broad overview. This is what machine learning is about. We're going to take this idea of intelligent machines. We're going to say, okay, we're going to try to make machines learn. And how do we do that? Let's set up these different ways of doing that. And currently, deep learning is the most popular way to do artificial intelligence, and all kinds of different applications are arising, and we'll talk about a couple of them. So if you want to study machine learning, there are actually a lot of really good resources to do so. So you can start out by self-studying some books. Here are a few that I would recommend. This is kind of the Bible of AI, which covers all of AI and not just the machine learning aspect of AI. Everybody has a copy of it. I don't know how much most people read of it, but it's great. It's very voluminous, and it's kind of like almost like a reference book. It's very large. My favorite introduction is actually by Bengio, and it's specific to deep learning. It's specific to machine learning, so it doesn't give you all of AI, but it gives you what is the most important AI technique right now. So I think that one's a really good place to start. Charnayak's Introduction to Deep Learning is kind of weird and quirky. It's very applied. He's a natural language processing guy, so I like his text. It's a good readable start. And then here's one that's kind of oddball. How Bodies Shape the Way We Think. Rodney Brooks is the one of the authors, and he was part of a group of people who had a movement a couple decades ago now that was pushing AI research into robotics. So robotics and having an actual body in the world became one of the sort of key aspects of artificial intelligence, getting away from sort of solving abstract problems and reasoning, and trying to do things like getting around in the world and sensing the world. So that's a good read as well. Some software. So most of the software for machine learning is written in Python, or at least the APIs are written in Python for almost all the dominant libraries. Python is very popular. You can use MATLAB as well, and MATLAB actually has a beautiful toolbox for doing machine learning, and there's some nice plug and play types of things in there. But at the same time, it's not a super active community of people using it, so you you kind of want to lean away from that, in my opinion. But it's a good piece of software too. TensorFlow is the most popular machine learning library. It's made by Google. You may have heard of it before. It makes the news occasionally. And you can use Python or other languages as an API for TensorFlow. So this is a really powerful machine learning library. A lot of cutting edge stuff is in TensorFlow. Keras is a sort of way to interact with TensorFlow at a little bit of a higher level, and you can use Python. So it's actually Keras is just Python, and it has sort of a high level API for TensorFlow. So you can use a lot of the really powerful tools in TensorFlow without having to roll your own every time. So it's kind of nice, especially when you're getting introduced to the subject. So some online learning places to start. The tensorflow.org website has some really good tutorials on it, so I would recommend checking that out. And Keras has an introduction for engineers, which I'm particularly fond of because there are a lot of computer scientists and computer engineers, but computing folks and data science folks who and statistics folks who work in this field, and you'll see kind of the engineering aspect or the engineering focused side, and you'll see the more computer science or data science folks. Everybody talks, but people have different motivations for learning it. So Keras has a nice intro there. Let's see here. Great. Guided study. If you want to learn machine learning, university programs will frequently have machine learning in the graduate side. So going to grad school in machine learning, there are a lot of different options. There are programs that are just specific to machine learning, but most of them are housed under data science program, computer science, electrical engineering, mechanical engineering. Those are the ones that I'm most familiar with. There might also be some activity in manufacturing as well, manufacturing engineering or other engineering fields. Machine learning is a broad field, so different programs have different foci, kind of like I mentioned before. That is reflected in programs as well as in the literature. Research projects. So although machine learning already has commercial applications, it's already being used commercially in products everywhere. Even everybody's got Siri in their pocket or something, Google Assistant or whatever it's called. So it remains an active research field, even though it's already deployed in many instantiations. So there are a lot of research projects working with machine learning. Academic and industrial labs perform fundamental and applied research, although the distinction between the two is starting to blur. You'll see academic institutions doing applied, industrial labs doing applied, industrial labs doing fundamental research, academic institutions doing fundamental research, and really the difference between those projects tends to be hard to determine sometimes. Most engineering machine learning research is in applications like robotics, machine vision, automated manufacturing, self-assembly, etc. So those are the types of things that most engineers who learn machine learning are interested in doing. And that's still usually considered to be a research problem. Of course, there are, for instance, manufacturing robots that already use like machine vision. So it's not just a research topic, but of course, that's where it starts. And a lot of projects continue to this day in terms of applications, which are barely scratching the surface so far. Our capabilities have increased so drastically in the last couple decades that the number of applications are vast for this technology. So I just wanted to talk a little bit about the program that we have, the one that I teach in. We have a master's in mechanical engineering program. There's the website. We have a hybrid remote option for folks who are a little further away from Lacey or Olympia area. 30 semester credits, 5 concentrations, great faculty, I like to think, small classes. And the 5 concentrations include this intelligent and dynamic systems concentration that I teach a lot of classes in. So you can do control systems, robotics, dynamic systems, machine intelligence or AI. And a lot of these control classes also will have a connection to machine learning nowadays. Computer science also has some courses. So we have a master's in computer science as well, and so you can take some classes in that if you'd like to have this concentration. So this is where we work on machine learning. So you can work with me and other faculty on exciting machine learning projects. Got to get the plug in, right? So turning now to the final thing I'll talk about, which is my AI research, which I think broadly fits under the topic machine learning for human thinking. So there's a lot to unpack here. I think it's there's 4 publications that I'm trying to fit into 2 slides. So I'll just try to kind of give you a little bit of a taste here. The first kind of thrust of this is uniting sort of a tagging information architecture where it's historically considered a flat architecture that doesn't have any structure vertically in hierarchies. And hierarchies, which are very familiar to us from everything, including, of course, our file systems would be the example that we've visualized the most. So I developed this sort of hybrid that is a sort of an organic hierarchy that comes from the set relationships implied in tagging systems. And so you can see a graph of the structure of an information architecture. And I also did some work on how to unite that with the flow of information. So you could think of a document as a flow of information that goes through your structure of information. And I worked on some ways to bring those together in terms of data representation and information representation. So I have lately started to apply that. I did a fuzzy logic version of that, so you can incorporate both textual data and, for instance, numerical data together. So that's what that paper was about. There was a patent there too, startup company, all that good stuff. I used to joke when I lived in Seattle that everybody you meet has at least one startup company. Machine learning for metastimuli is what I've been working on lately. So one of the things that I've started to do is building on that information architecture that I've worked on, which is the main idea behind it was to help enhance human thinking and creativity. And I started to use this I want to close the loop where people can have their information architecture, their personal information management system, or PIMS, what they're experiencing in the world, what they are maybe watching in a video lecture, for instance, could get filtered through a machine learning algorithm and correlated with their personal information management system, the structure of it, and go all the way to a haptic feedback device for them. So mostly I've been focusing on just the machine learning aspect of it and not specifically which mode of haptic feedback, which of course haptic feedbacks, I think a lot of people are familiar, but haptic feedback for a video game controller would be the vibration, or for your phone would be the vibration of your phone. So haptic feedback is making its way into different places in our lives, and there has been some research in how it can enhance our ability to learn if you have correlations. So I just presented a paper on this, and it uses two different neural networks. One of them is a word embedding, so natural language process sort of neural network, and then the other one is one that trains on the classification of a given atom of information or chunk of information. So text is the one that we're starting with. And this is kind of the outline of how that would work. So you'd get a stimulus as a user directly, of course, like you'd hear the video lecture. And then you would also get a machine learning filtered through your own personal information management system, actuated haptic metastimulus. So it would be correlated with where that occurs in your personal information management structure. So here's an example of how that would work. We've got this big graph of your personal information management system that people have, and they're listening to something and it lights up in these different nodes. So this is a small sort of toy problem, so you can see it. But you can see that this graph, it's sort of like a hierarchy, but it's actually a graph structure, has a certain sort of recognizable structure to it. Like this branch, the A branch, the green, is sort of a distinct branch. The C branch is sort of a distinct branch, and the B branch is sort of a distinct branch. They share a common node here. And what we can do is we can do a principal component analysis on a graph, this graph. We can compress it down or project it down to lower order spaces. So we usually, for visualization purposes, shoot for R2, which is what this graph represents. So we compress it down to R2, and we see where would they lie in R2, and you see that the green branch is visible here, the red branch, the blue branch, and you see the purple shared node is in between those two branches. So what you do is you take this graph representation, which doesn't have any real metric on it. It isn't in a metric space that you can measure, and put it onto Rn, whatever R you would like. We've developed an algorithm that does this compression. Now, one of the things that the compression allows us to do is we can choose. Our actuator could have maybe 3 different axes. Maybe it's distance longitudinally on your arm, and the other way around the hoop of your arm. The 2 different axes there, and then maybe vibration frequency or duration or something like that. So there are different modes of haptic feedback, and so the more dimensions that you can increase your stimulation in, the more information you can represent effectively in a projection. So we did this work, and we've got a couple grad students working on this now. So I think I'm at time. So here's how to contact me. This is my website. This is the St. Martin's website, and I'll have, I guess, I don't know, Alexander and Matt, if you guys could send out my presentation, and then later on, and then these are just the references for you, so you can get this PDF later. It's available online. So yeah, now I'm happy to entertain questions. Thanks everyone. Thanks for inviting me. Thanks. Yeah, it was a pleasure. I really enjoyed it. It was great being here.